My name is Laura Lyman, and I'm a PhD candidate at Stanford University at the Institute for Computational and Mathematical Engineering. It's great to have you here. I am thrilled today to present this Women in Data Science workshop on linear algebra. This is the third installment in the series, so if you need a refresher, go ahead and watch the previous two videos. Otherwise, I'll be responding to questions in the chat, and I'll be available to answer questions live at the end. Today, I hope you'll realize that linear algebra is not only a beautiful subject of mathematics, but it's one that lives at the heart of all the information around us. Please enjoy. In several situations in science and engineering, we will find ourselves with measurements for some output parameter y against a certain explanatory variable, or input parameter x. For example, x could represent the number of years you have been learning data science, and y could denote your interest in this workshop. Sometimes, a specific relationship between variables can be difficult to spot. However, in other cases, we're lucky, and we can observe an approximate linear dependency between the variables that we are examining. And if so, we can apply a simple linear regression scheme, such as ordinary least squares. Often, we'll actually have multiple samples measured for a variety of different properties. For instance, we could have several patients coming into a hospital, each of which has various attributes that are recorded. Now, when we have only two variables, such as weight and height here, all is well. We can plot one variable against another in the classic fashion. For three variables, the result is analogous. We generate some kind of 3D image. For 4 or 5 variables, perhaps we get creative. We assign a color gradient to encode the additional information, say resting heart rate, and then maybe at some point we use a different type of marking pattern on our plot to additionally denote another dimension. But at some point, we add so many variables that this becomes untenable. Namely, we don't have a meaningful way to depict all of the information graphically at once in a manner such that a user can actually glean information from it. So what do? Well, typically, we'll start examining different explanatory variables pairwise. However, at best, this is a cross-sectional understanding of what we ultimately want to be a big-picture characterization of our data. If we could reduce the number of variables that our output or response parameter y depends on, then our problem would become computationally easier, and perhaps more importantly, we could understand all of this information in a clear-headed fashion. For initial dimension reduction, we might ask questions about linear independence. Say, are any of these explanatory variables a linear combination of the others? In which case, we could disregard the variables that represent some kind of redundant information. In the context of regression, we might wonder if some of these explanatory variables are more important or influential on our measured output, in which case, we can shift our focus to the parameters that actually matter. These are important considerations that many are familiar with. But another fascinating and powerful tool in data science that is sometimes less known performs dimension reduction in a different manner. That tool is called principal component analysis. Principal component analysis, which I'll often abbreviate as lowercase pca, is a linear model that summarizes data in terms of so-called feature variables, which I'll refer to as V1 through Vp. Feature variables are sometimes also called principal components. Each feature, Vj here, is itself a linear combination of the original n explanatory variables, x1 through xn, that were all measured. Though the key here is that we want p to actually be less than n. That is the dimension reduction part. We can think of this as a change of coordinates that re-expresses information in terms of a new, more minimal coordinate basis system. Well, as a contrived example, suppose we have the perimeter of a rectangle as the response variable y, and we are measuring y in terms of two variables, width and height. We consider several rectangles and measure their perimeters by hand. And with these variables, we of course know that linear regression would give us that the final perimeter y is 2 times the width plus 2 times the height.
Since width and height are clearly independent as explanatory variables, and since both are equally important for calculating the parameter y, this is as far as we can reasonably go in terms of dimension reduction, if using linear regression. However, notice that we can immediately factor out a 2 in our expression for the perimeter. And if we define a new variable, call it v1, as the sum of the width and height, we now have that our observed parameter y is a function of only a single variable. Effectively, we've reduced the dimension of our problem from 2 to 1. This is an application of principal component analysis. To reiterate, unlike linear regression, principal component analysis isn't asking whether x1 the width or x2 the height is less meaningful or important than the other for explaining the output. Instead, it says that for calculating the perimeter, we don't necessarily care about width or height individually, but instead their interaction or relationship, encoded by x1 plus x2, is what characterizes the property we're interested in. You might think, okay, Laura, this makes sense in the rectangle example, but in the real world, does this actually happen? And the answer is yes. You'll be surprised. We can do this all the time, and PCA is surprisingly effective. Now, in addition to considerations around dimension reduction, if you perform a quick Google search on PCA, you'll likely see discussions about orthogonal projections, best linear fit, or statements mostly about how PCA, quote-unquote, fully captures the diversity of the data. While these statements might seem incongruous at first, how would those concepts even fit together? We can step through and address them one by one. First, a best linear fit and orthogonal projections. Okay, this we can get some intuition behind. Let's consider the original example. And suppose we are examining the relationship between a resting heart rate, measured in beats per minute, and diastolic blood pressure. If you're curious, this data, while synthetically generated, was based on actual means and standard deviations measured in the following paper. Now, the point cloud was translated to the origin, since of course we cannot literally have negative values of x and y in this context. And that's okay, because again, PCA is more concerned about the values of the data points relative to one another. Namely, despite translating, this one is still the leftmost, this one is still the largest on the x2 axis, these two are still close together and in the middle, etc. And of course these justifications can be made mathematically rigorous. Now, roughly speaking, for any kind of linear modeling, we are selecting a line that minimizes the error between the actual y values, shown in blue, against the y values predicted, that is, the red line. However, there are many ways to measure which line is best, which one is more appropriate, and which one minimizes error. When we regress y and x, for instance, the ordinary least squares fit is the one that minimizes the sum of squared vertical distances between the true data points and their estimates on the regression line. Similarly, if we regress x on y, we'll observe that the regression line is the one that minimizes the horizontal distances, squared and summed. Accordingly, we can conclude that our metric for defining error is somewhat subjective. There are several reasonable alternatives. In this case, you'll notice that when we discuss PCA, we're never actually specifying whether one variable is regressed against another, which is already an indication that we have some kind of symmetry. In particular, principal component analysis selects the linear fit to be the one that minimizes the orthogonal projections, or perpendicular distances, from every single data point to the regression line.
2. Maximized variance, or accounting for the most variation or diversity in the dataset. From statistics, recall that the computational variance for a measured parameter is the average spread, or squared standard deviation, from its mean. PCA seeks to find the linear fit that maximizes the variance of the projected data. In other words, principal components are properties constructed such that they differ as much as possible across our measurements. Now, why would we do that? Well, imagine if you came up with a property that was nearly the same across all data points. That information would not be very useful, would it? Finding a property or feature that accounts for the most variance in the data captures more information about how the explanatory variables in question relate to one another. It is not immediately obvious by any means how maximizing variance is compatible with finding the linear fit that minimizes orthogonal projection error. That is, how can PCA accomplish both goals at once? The punchline is this: it turns out that minimizing orthogonal projection is equivalent to maximizing variation across the data set. We can witness these principles in action and the graphs here for our medical example. The black dots are data points, and their orthogonal projections, shown via the dashed red lines, indicate their estimated or predicted values via the linear fit. The direction of the proposed linear fit is rotated, and the red segment shows the spread of the projections in the linear model. Pay attention to the length of this red segment. Namely, it contracts, representing that there's less variance, precisely when the orthogonal projections are larger, and when the orthogonal projections are smaller or minimized, the variance or spread actually grows. To truly understand why these two optimization problems are yielding the same goal, I'll zoom in. Let W denote the proposed vector selected by PCA, here in gray. Now let's look at a single data point, say the ith one, x sub I 1, x sub I 2, which I've shown in blue. The red here indicates the standard deviation of the estimate of our data point from the mean, which in this case is the origin, since we've centered our point cloud of data. The orthogonal projection error is in purple. The hypotenuse of this triangle is the length of a given data point vector, which has to be fixed. It remains the same no matter how we rotate the proposed fit vector W in gray. So by the Pythagorean theorem, in order to maximize the spread for this single data point, that is the red, we are forced to minimize the orthogonal projection error in purple and vice versa. Since variance will involve these red portions for every data point to be squared and summed, and similarly, the total sum of squared error residuals will involve all of these purple segments, we can see that maximizing the variance in our linear model overall becomes equivalent to minimizing these projection errors simultaneously. Up until now, we have only explained what PCA does, but not how exactly it performs. To better understand PCA, we will review or learn about special vectors called eigenvectors and scalars called eigenvalues that are associated with every square matrix. These vectors and scalars, the eigenfamily, if you will, work together to describe key properties of a matrix structure and how the matrix operates. Definition. For a square matrix A, we say a non-zero vector V is an eigenvector of A if A times V is equal to lambda times V for some scalar lambda. Take note, the left-hand side has matrix by vector multiplication, while the right-hand side is just scalar by vector multiplication. Here, the lambda, which is just some number, is called the eigenvalue associated with the eigenvector V. This is a symbolic statement, but let's see if we can grasp what it means intuitively. Well, it says that given some non-zero vector V in space, A times V, that is, A acting on V by multiplication on the left, produces a vector that is just a scaled version of the original input. The eigenvalue is the factor by which the eigenvector is stretched or squashed during the linear transformation. For instance, take the 2 by 2 matrix displayed here, which we will call A. We can verify that A times the vector 1, 1 simply equals 3 times 1, 1. This means that 1, 1 is an eigenvector for A with an eigenvalue lambda equal to 3. And exactly as we see here in the two graphs, lambda is the factor by which the eigenvector was stretched. Similarly, if we perform the multiplication A times 1, 0, we're left with negative 2 times 1, 0. This means that 1, 0 was also an eigenvector, only now with eigenvalue lambda equal to negative 2. This eigenvalue is reflected graphically. Given the original vector 1, 0 in red, denoted here by v, A times v flips the eigenvector across the y-axis and scales it by 2. What can we learn from our eigenfriends? Eigenvectors are a critical tool for understanding what exactly a linear transformation is doing. They are the axes along which a linear transformation's behavior is simple, namely, we're only scaling or stretching along a single line. The eigenvalues give you the factors by which the scaling or stretching occurs. For example, the blue dots here represent randomly generated vectors within the unit circle. We can envision the vectors starting from the origin. In code, I then multiplied every one of these data points by our matrix A that we've seen before, negative 2, 5, 0, 3. We can immediately observe that the output looks like an ellipse. But how did that happen? Well, in particular, the vectors in purple, that is, those aligned with the first eigenvector, 1, 1, were all stretched by a factor of lambda equal to 3. Similarly, we can examine what occurs along the eigenvector 1, 0. These points were doubled in length and flipped across the y-axis, which is consistent with the eigenvalue lambda equal to negative 2. The more linearly independent eigenvectors we have, the more directions along which we understand the behavior of a given linear transformation. At this point, we have the needed vocabulary for examining an essential matrix factorization. Let A be a square n by n matrix with n linearly independent eigenvectors, as we just discussed. Then the eigendecomposition, or spectral decomposition as it's sometimes called, of A is the following factorization. A is Q times lambda times Q inverse, where Q here is an n by n matrix whose columns are the eigenvectors of A. And of course Q is invertible since we have full column rank. Lambda is a diagonal matrix whose diagonal entries are the eigenvalues of the inputted matrix. Now, when it's possible to factor a matrix in this manner, or equivalently, when a matrix has n linearly independent eigenvectors, we say that the matrix is diagonalizable. Since we've examined several theoretical properties, let's briefly turn to some practical applications. Now, the eigenfriends can give us seemingly endless possibilities in terms of how we can use them in day-to-day life. For instance, eigenface is the name given to a set of eigenvectors used in the computer vision problem of human face recognition. As another example, the order in which your search results appear in Google is determined by computing an eigenvector. At least, originally it was in Google's PageRank algorithm. And of course, for the method that catapulted us into this discussion in the first place, eigenvectors and values are at the heart of principal component analysis. Now we have the foundation to return to our exploration of PCA. So suppose again we're taking measurements of m total properties, and we measure each one of these properties n times. Then X is going to be the m by n matrix such that X sub ij is the jth measurement of the ith property. Sometimes X is also called a design matrix. So continuing with our example, when n is 2, we can take this heart rate and blood pressure data and simply encode it into a matrix by putting the corresponding columns over here. From here, we then define the covariance matrix, capital C, to be X transpose times X. Note that we've omitted the classic scaling factor of 1 over n minus 1 that usually appears in the definition of a covariance matrix in statistics. However, for the purpose of interpreting PCA, we can actually ignore this factor. That will be discussed later. Now that the covariance matrix has been defined, and we have a foundation in terms of understanding the eigendecomposition, we can relate the eigendecomposition of this covariance matrix back to the SVD of the original data matrix. So in particular, we have these factorizations, and let's see how they relate. Well, for one, the columns of Q, down in purple over here, are the eigenvectors of the covariance matrix C, and those are precisely the same columns of the orthogonal matrix V that appears in the singular value decomposition of our original matrix X. In addition, we can relate the entries of capital lambda to those of capital sigma, namely the eigenvalues of our covariance matrix C are equal to the singular values squared. Now, if you're very observant, you might wonder why we're guaranteed to know that V is orthogonal if V and Q simply share the same columns, and Q in the eigendecomposition isn't always orthogonal. Well, this happens to follow from the fact that C is a symmetric matrix, meaning that there exists an orthogonal basis of eigenvectors that can span our n space. But that's a technical aside. Given this information, and without further ado, we can finally assess the PCA algorithm directly. The process is as follows. First, we populate an m by n data matrix, capital X, where again, m is the number of measurements and n is the number of explanatory variables, as we did in the example before. Then, we subtract off the mean for each variable or property being measured. In our case, the columns of our data matrix X. Then we calculate the principal components and PC scores, and we'll explain what those are. But essentially, we have two options for this third step. Either we can perform an SVD on X directly, or we can factor the covariance matrix C with an eigendecomposition. For a note on common vernacular, I'll mention this. Throughout this workshop, we've used PCA, all lowercase, to refer to this overarching framework. However, some people will use PCA, which I would capitalize in that instance, to refer specifically to using this process with step 1 of part 3. That is, they are inherently assuming that when we're going through and computing the principal components, we're doing so with an eigenvalue decomposition. Now that we know how to execute the PCA algorithm step by step, we can consider another very exciting real-life example. Say we are researching breast cancer. We are trying to understand the key characteristics of what makes a tumor cell benign or harmless versus malignant, that is, potentially dangerous. The following data from the University of Wisconsin is taken from digitized images of fine needle aspirates, FNA, of breast masses for various patients. The features describe characteristics of the cell nuclei present in the taken images. In the study, there are many traits of a tumor that we can observe and measure, The following matrix is comprised of the data for the first 50 patients who have a mix of benign and malignant tumors. For simplicity, suppose we only consider the following 9 properties in the dataset. For example, radius mean is the average distance from the center of a breast mass to points on its perimeter. Texture mean is the standard deviation of the grayscale values of a given digitized image. The perimeter mean will be the average perimeter, and etc. Recall that the PCA procedure is as follows. First, we're going to populate the data matrix, or the design matrix, capital X, with m measurements of n total explanatory variables. Then we subtract off the mean for each measurement type, in our case, each column of the data matrix X. And then we have some choice. We're going to calculate the principal components and PC scores, where we can recall that the principal components are the eigenvectors of the covariance matrix C, and the PC scores are the eigenvalues of the covariance matrix C square rooted. Now that we have options for which factorization should be used to achieve this eigeninformation, we can go through each process and see how it goes. So first, let's use the SVD. The PC scores are going to correspond to the non-zero entries of sigma, ranked from largest to smallest. The larger the PC score, the more its corresponding principal component characterizes the dataset. So here we can look at the top 2 PC scores, for example. We can see that the first one is very big, it's around 2067, and the second one is about 28. And these 2 PC scores correspond to the first 2 columns of V. These are our principal components, and we will interpret them later. Now, alternatively, we can use an eigendecomposition on the covariance matrix. Now, the reason that the usual 1 over n-1 factor is omitted is that it would have been absorbed into the diagonal matrix capital lambda anyway, giving an identical interpretation of the dataset. So what do I mean? Well, in order to determine which eigenvectors are the principal components, we're going to look at which PC scores are largest. And if we scale all of the PC scores by the same factor, that's not going to affect their ordering relative to one another. So here we compute the covariance matrix, which will be 2 by 2. And then from looking at lambda, we can read off the same 2 PC scores as we did previously. Well, this is a sanity check, that with either technique, we're getting the same information. Now comes a tricky part, trying to make sense of the principal components. For the first principal component, we can see that it's dominated by this 4th entry, with magnitude that's nearly 1, where we note that the maximum magnitude of any entry in V can be 1, since V is an orthogonal matrix. This means that the first principal component is best described by the 4th feature, which in this case is area mean, i.e. the average 2D area of the breast mass in a digitized image. For the second principal component, observe that it is biased towards its second and third variables, and all the remaining values are at least an order of magnitude smaller. This means that the second principal component, or a new characteristic describing these masses, is a linear combination of texture mean and perimeter mean. The variable texture mean, as I said previously, is the standard deviation of the grayscale values in the image, since topography, or texture, is indicated by darker or lighter pixels. Since this involves standard deviation, it means that a breast mass with a large texture mean
isn't necessarily large or tall, rather its texture is non-uniform and inconsistent. Heuristically, we can imagine this as spikiness, or an ill-defined and inconsistent border in its third vertical dimension. What about the variable perimeter mean? Of course, a tumor with a larger area will necessarily have a larger perimeter. However, for the characteristic the second principal component is describing, we know that perimeter mean indicates information that is somewhat independent of the tumor's area. For otherwise, the fourth entry of this eigenvector, which corresponds to area mean, would be larger in magnitude. So how can we vary the size of the tumor's perimeter while minimally affecting its area? One way to increase the perimeter without increasing the area is to give the mass tall and skinny spikes protruding from its border. This way, the perimeter is increased by traveling up and down the spikes, while minimal area is gained since these spikes are so thin. In this sense, perimeter mean on its own can be a metric for how much zigzagging occurs on the breast mass's border. Therefore, the second principal component can be described overall as spikiness or fuzziness of the tumor's border, whether in the two-dimensional section or whether in its vertical direction. What's amazing is that principal component analysis told us these characteristics directly. Again, this is real data, and the interpretation here isn't biased by any prior medical knowledge. However, if we then Google defining characteristics for determining benign or malignant breast tumors, we can see right away that two important hallmarks are the tumor size, i.e., its area, and whether it has an irregular shape with spiky or fuzzy edges. Now, note that the top PC score, again, above 2000, is an order of magnitude larger than all of the other singular values. This means that while overall spikiness or fuzziness is the second most important attribute, ultimately, the first principal component, the average tumor area, has the most influence over characterizing the dataset as a whole. As of now, we've addressed how principal component analysis selects linear combinations of the original explanatory variables in such a way as to form new features that account for the maximum possible variation across the dataset. And by accounting for this maximum variance, PCA simultaneously minimizes orthogonal projection error. However, we have not addressed why the principal components are the eigenvectors of the covariance matrix C. To understand this portion, we have to look at our model mathematically. In particular, consider the zoom-in that we explored previously. The ith data point, x sub I1, x sub I2, is denoted here in blue. As before, the W in gray denotes the proposed linear fit, and ultimately, we're going to adjust W until it coincides with the principal component that has the properties that we're looking for. The red segment here is the deviation of the ith data point from the mean, which in this case is the origin, since we've centered our point cloud of data. Immediately, we have a right triangle. Now, we know if we denote the angle between the ith data point and W as theta, that the cosine of that angle, adjacent over hypotenuse, can be used to represent the red segment as cosine of theta times the norm of the ith data point, x sub I1, x sub I2. From here, perhaps, we can recall from the first workshop in this series that we can write an expression for the angle between two vectors in space. Namely, cosine of theta is going to be the dot product
of our ith data point, x sub I 1, x sub I 2, with the soon-to-be principal component vector w, all scaled by the lengths of these two vectors, which we have in the denominator here. So if we substitute in this entire expression into what is our calculation of the variance or the deviation of the ith data point, we have some cancellation and immediately get an expression of the following form. So again, we have a scalar 1 over the 2 norm of w times another scalar, which is formed from the dot product between the ith data point, written as a vector here in blue, with w. But we can take this even further. So now let's consider all of the blue data points, not just the ith one. If we put all of those data points into our data matrix or our design matrix, capital X, we would have something of the following. And we know from matrix vector multiplication that the output of multiplying capital X by W is formed by taking the dot product of every row of capital X with W, which is to say that we're repeating our computation for this segment in red for several different data points. The output of this entire expression is going to be an m by 1 vector, whose ith component is precisely the dot product of the ith data point with the vector w, with this scaling factor in front of 1 over the norm of w. Now that we have this m by 1 vector, let's give it a name. Let's call it z.
Something miraculous then happens when we consider the 2 norm of this vector z squared. Namely, if we want to consider the total variance that comes from selecting our linear fit to be w, we have to take the sum of all of these red components squared, because that is the definition of computational variance. So in particular, in order to get the total variance, we are doing this sum of squares, ignoring a proportionality constant for now, and that is exactly the 2 norm of z squared, which we have just calculated to be the 2 norm of capital X times w, all squared, and then again scaled in the front by 1 over the norm of w squared. However, we know from the definition of the 2 norm that this fraction is precisely w transpose times x transpose x times w, all in the numerator, which immediately indicates that our matrix C is popping up. At this point, we want to select w to be the vector that maximizes the total variance. And we can maximize the total variance by maximizing this expression that we've calculated here.
Finally, we have that w is going to be the argmax of this numerator and denominator, w transpose cw over w transpose times w. Now remember, the argmax is the maximizer of this whole expression. That is, it's the w we need to plug in such that this whole fraction is as large as possible. Now, this last part is a non-trivial proof, and I won't get into it here.
This is typically a problem, for instance, in Homework 1 in Stanford CME 302 class, or graduate level numerical linear algebra. So it does take some thought, and it ends up requiring the use of the SVD. But regardless, the punchline is this. This entire expression is maximized at the eigenvector of our covariance matrix C corresponding to C's largest eigenvalue. To summarize, by requiring the principal component W to maximize variation explained in the dataset, we were forced to select the principal component to be an eigenvector of C. The high-level takeaways are this. Principal component analysis selects a linear model that simultaneously minimizes orthogonal error while encapsulating the diversity or complexity of a dataset as much as possible. It is a critical tool for dimension reduction, and it differs from linear regression, that is, ordinary least squares mostly, even in low-dimensional problems. PCA can be executed with an SVD or eigenvalue decomposition. There is choice. And finally, it helps identify and characterize patterns in all of the information around us. Thank you, and please reach out if you have any questions.